Okay, so in this lesson, we're going to be discussing some mathematical applications of Taylor and Maclaurin series. Now, in a previous lesson, we have introduced Taylor and Maclaurin series, and we have seen how we could set up the expansions corresponding to these series that represent given functions. And in another lesson, we have discussed the Lagrange form of the error term that is obtained by approximating functions using these series. However, in this lesson, we're going to be discussing some mathematical applications or different ways we can use Taylor and Maclaurin series. For example, here we have approximating functions, so we can use these type of series to approximate functions at given values. We could also use these series. We're going to see in a bit that we can use these series to approximate limits of functions in addition to approximating solutions to differential equations. So over here, if I were to start with this first example, I need to approximate ln of 1.1 using a third-degree Taylor polynomial and determine the maximum error of this approximation. Now, so I need to start by introducing a function over here that would help me approximate ln of 1.1. Naturally, since I want to approximate ln of 1.1, so I think of introducing my function as a ln function. So, for example, since I need to approximate ln of 1.1, I could think of introducing f of x as ln x. Or since 1.1 could be seen as 1 plus 0.1, so you could also choose to go for f of x equals to ln of x plus 1. So over here, in using the first function to approximate ln of 1.1, you'd go for f of 1.1, while if you were to be using ln of x plus 1 to approximate ln of 1.1, you'd go for f of 0.1. So it really depends on how you choose your function, as long as you'd eventually end up with a value of x that would help you approximate ln of 1.1. It doesn't really matter, the choice is up to you. However, we know that a Taylor polynomial has to be centered at a given value. So the value that the polynomial is centered at really depends on the choice of your function. If you were to go, for example, for f of x equals to ln x. Now, f of x equals to ln x, to represent that by a Taylor polynomial, you cannot possibly center the polynomial at 0, because f of 0 is not defined. 0 is outside the domain of this function. So if you were to go for f of x equals to ln x, you'd need to center your Taylor polynomial at a real number different than 0, or that is not negative as well, since ln x cannot take negative numbers. So over here, if you were to go for f of x equals to ln x, it's better to consider to have your polynomial centered at 1, for example, because f of 1 is ln 1, which is 0, then the first derivative is 1 over x. At 1, it's 1. So centering the polynomial at 1 would give you easier coefficients to work with. However, if you go for f of x equals to ln of x plus 1, now that is a polynomial that you can center at 0, because you notice that the values that you obtain here for x equals to 0 are the values you obtain here when you center the polynomial at 1. So for example, f of 0 here is f of 1 there, etc. Similarly for the rest of the derivatives. So it's really up to you, but watch out for the value that you center your polynomial at. It has to be a value that the function and all its derivatives are defined at. So I'm going to go for f of x equals to ln of x plus 1, because if you have the choice to center your Taylor polynomial at 0, it's always much easier. So if I go for f of x equals to ln of x plus 1, so f of 0 is ln 1, which is 0. So your first coefficient of the Taylor polynomial is 0 over 0 factorial, which is 0. Then going for the first derivative. Now this is in the form ln u, so the derivative is 1 over u times u prime. So it's 1 over x plus 1 times u prime. If u is x plus 1, u prime is 1. So which leaves you with a first derivative equals to 1 over x plus 1. So evaluating the first derivative at 0 would also give you 1, leading to a second coefficient of 1 over 1 factorial, which is 1. As for the second derivative, now that is in the form 1 over u. So 1 over u has a derivative of negative 1 over u squared times u prime. Again, u is still x plus 1. So the second derivative is negative 1 over x plus 1 all squared. So that would lead you to a second derivative at 0 equals to negative 1. And the third Taylor coefficient would be negative 1 over 2 factorial, which is negative 1 over 2. Now, they want the polynomial to the third degree, so I still have one derivative to find. So this is in the form 1 over u to the n. Now, just recall that functions in the form 1 over x to the n have a derivative of negative n over x to the n plus 1. So over here I have it in the form 1 over u squared. So the derivative is a negative 2 over x cubed for n equals to 2, and of course times u prime, where u is x plus 1, so u prime is 1. So negative 1 times negative 2 would give you a 2 over x plus 1 all cubed. So let me just separate this rule. Okay, so the third derivative at 0 would actually give you 2 over 1 cubed, which is a 2. So the fourth coefficient, which is a3, is 2 over 3 factorial, which is 2 over 6. So 2 over 6, which is 1/3. So now I can write my polynomial, which is f of x equals to the constant 0 plus the second coefficient times x, so that would be an x, the third coefficient times x squared, and the fourth coefficient times x cubed. So that is the third degree polynomial, Taylor polynomial, centered at 0. However, if you decided to go for f of x equals to ln x and center that polynomial at 1, keep in mind that maybe the derivatives will be easier to find. However, after finding the corresponding coefficients, the coefficients would be multiplying x minus 1 all squared, x minus 1 all cubed, because that polynomial would be centered at 1. So over here, now that I have found the third degree Taylor polynomial centered at 0, representing the function f of x, I could approximate ln of 1.1. Remember that my function is ln of x plus 1, so ln of 1.1 is obtained for x equals to 0.1. So over here I need to find f of 0.1, and I do that by replacing x by 0.1 in the given Taylor polynomial. Sorry, this is 0.1 cubed. Okay, so evaluating that on my calculator, so I'd go for the run menu. So over here I have 0.1 minus half times 0.1 squared, and then plus 1/3 times 0.1 cubed. Okay, so that would give me 0.0953. So over here, f of 0.1 would approximately be 0.0953. Let me just double check here. So this is to 3 significant figures. So this is an approximate value of ln of 1.1 to 3 significant figures using the third degree Taylor polynomial. Now, however, I need to determine the maximum error of this approximation. So my question is not done yet. I need to approximate ln of 1.1, which is what I just did using a third degree Taylor polynomial, but I need to determine the maximum error of this approximation. So what is the error obtained? What is the maximum error obtained by doing this approximation using this third degree Taylor polynomial? So what we need to do here is use the Lagrange form of the error term. So I'm going for R3 of 0.1, since over here x for relative to this function, x is 0.1. So R3 of 0.1, it's R3 because it's the error term corresponding to a third degree polynomial, Taylor polynomial. So R3 of 0.1, according to the Lagrange form of the error term, that's the fourth derivative at t divided by 4 factorial times the value of x, which is 0.1 to the power of 4, where t is between 0 and x. So t is between 0 and x, which is 0.1. So over here, I need to find the maximum error obtained. So over here, by finding the fourth derivative. Now, if I go back to the third derivative was 2 over x plus 1 all cubed. So the fourth derivative would actually be applying the same rule we have here. So it's in the form 1 over u cubed. So the derivative according to this would be negative 3 over u to the power 4 times u prime, of course multiplying 2. So 2 times negative 3 is a negative 6. Divided by x plus 1 to the 4, of course, times u prime, and u here is x plus 1, so u prime is 1. I forgot the x here. Okay, so R3 of 0.1 would actually be negative 6 over t plus 1 to the 4 times 0.1 to the 4 divided by 4 factorial. So simplifying this just a little bit, so R3 of 0.1 would actually be, now over here we have negative 0.1 to the 4 divided by 6 over 24. 4 factorial is a 24, so that's 24 into t plus 1 to the 4. Now, just studying this function, and don't forget that this function is defined for t between 0 and 0.1. Let's just call this function g of t for the moment. So remember that our aim here is to determine the maximum error that could be obtained by this approximation. So over here, in order to do that, I need to determine where g of t is maximum. Now, over here, you'd notice that the error term is in fact a function in the form negative 1 over x to the 4. Of course, the coefficients would just stretch vertically or horizontally. The curve t plus 1, it would just shift the curve 1 unit to the left. But however, the coefficients do not affect the sense of variation. So over here, I'm going to use my GDC. Going back to the menu, now I'm going to go for graph, and I'm going to just graph the standard function that links to this one, which is -1 over x to the, sorry, I'm just going to use x, this one, alpha x, and to the 4. Since the other coefficients, the 0.1 to the 4 and the 24 and the t plus 1, we just transform the function by stretching it and translating it, but they do not affect the sense of variation of this function, y equals to -1 over 4. So over here, before we draw this, let's just, okay, so 0.2, -2, I think it should be fine since we're dealing with small values here. So I'm going to go for draw. Okay, perfect. So you can see that the function is in fact increasing. So g of t being increasing over the interval 0, 0.1, in that case, the maximum value of g would be at 0.1. To make sense of it, if we were to just draw a small sketch, if this is the interval 0 and this is the interval 0, 1, then over here, if I were to draw the function over the interval 0, 0.1, we've just seen that it's increasing. So the function being increasing, let me just bring this up above the x-axis. So the function being increasing, that you'd notice that the highest point on the curve, the maximum of the curve, lies at the upper bound, which is at t equals to 0.1 here. So this is the maximum we are looking for. So g of t is max for t equals to 0.1. So over here, the maximum error would be for t equals to 0.1, which is R3 of 0.1, which is equals to -0.1 to the 4 over 24 times 1.1 to the 4. So evaluating this on my calculator, so going back to the menu. So going back to the menu would actually help me evaluate this. So okay, so we have the negative is outside the parentheses. I'm sorry about that. Okay, so the negative is outside the parentheses. So it's -0.1 to the 4 divided by 24 times 1.1 to the 4, which is -2.84 times 10 to the -6, which is approximately -2.84 times 10 to the -6. So that is the maximum error that you would obtain by doing this approximation. Now, over here, by the way, the following digit is a 5, so we could have just taken this to be -2.85. So another application here of Taylor and Maclaurin series would be helping me approximate limits. So here, if we look at this function, we'd need to evaluate the limit when x is approaching 0 of cosine x minus 1 minus x squared over 2 over x to the 4. Now, I believe there is a typing mistake here. I believe this should be a plus x squared over 2. Okay, now looking at this limit, if we replace x by 0, we end up with 0 over 0, which is an indeterminate form. Now, there are methods to cancel indeterminate forms, which, for example, over here we could be using L'Hopital's rule. However, now in this example, we're going to see how we could use Taylor and Maclaurin series. Now, looking at the function, I'd notice that everything other than cosine is already a polynomial. -1 plus half x squared is a polynomial, and at the denominator x to the 4 is a polynomial. So cosine x is the only term that remains not a polynomial. So over here I need to determine a Taylor or a Maclaurin series that represents cosine x. Now, in our previous lesson, when we introduced Taylor and Maclaurin series, we have already generated the Mclaren series that corresponds to cosine x. So over here, if I just use that expansion, if you need to recall how this expansion was generated, you can just refer to the previous lesson. So cosine x is the sum when k goes from 0 to infinity of -1 to the k times x to the 2k over 2k factorial. Now, the Mclaren series corresponding to cosine only holds the even exponents of x. However, the Mclaren series corresponding to sine holds the odd exponents of x. Anyway, if we get to this limit, if we call this limit L, so L is the limit when x is approaching 0 of. So replacing cosine by its Mclaren expansion. So for k equals to 0, it's a 1. For k equals to 1, it's a -half x squared. For k equals to 2, that's a +1 x to the 4 over 4 factorial, which is 1 over 24 x to the 4. Okay, then for k equals to 3, we'd obtain x to the 6 divided by 6 factorial. So it's -1 over, let me just leave it as 6 factorial now, x to the 6, etc. That expansion could keep on going infinitely. Then I add the remaining two terms that we have here, which is -1 plus half x squared. Let me just extend my fraction bar, divide by x to the 4, and then move forward. So over here you'd notice that first we do have similar terms that cancel out. For example, 1 cancels out -1, and -half x squared cancels out half x squared. So I'm left with these terms of the expansion. Now you'd notice that these two terms are terms of the same degree. However, starting from k equals to 3 all the way to infinity, you'd notice that these exponents, these are terms where the degree is greater than that of the denominator. So over here, we could just start by splitting our fractions. Since I only have a single term at the denominator, I could start by splitting the terms corresponding to my fraction. So over here, 1 over 24 times x to the 4 divided by x to the 4 would give me 1 over 24, negative 1 over 6 factorial x squared, etc. So now that I have split my fraction, you'd notice that this is the only term that does not contain x. All the other terms would have an x in them. They would consist of a power of x. So by setting x equals to 0, all of these terms would eventually be equals to 0, which leaves me with a limit equals to 1 over 24. So 1 over 24 would actually be an approximation to this limit using the Mclaren series corresponding to cosine x. Now, in this last part where we will see how we could approximate solutions of differential equations using Taylor and Maclaurin series as well. So over here, I'm given the differential equation, which is dy over dx minus y tan x equals to cosine x. And I do have the initial condition, which is 0 minus pi over 2. Now I need to find a Mclaren series. Now Mclaren series, it means that the series is centered at 0 for y up to and including the term in x squared. Now there are several ways that we could be solving this differential equation. However, sometimes we come across differential equations that are really hard to determine the solution to, especially if we come across integrals in the process that cannot be integrated using differential calculus. So in that case, we have Taylor and Maclaurin series as an alternative to help us approximate solutions to these differential equations. So over here, my differential equation is y prime equals to y tan x plus cosine x. Now, so there is an alternative way in order to rewrite my differential equation. Now, why is it so? It's because I need to determine the values of the Taylor polynomial corresponding to each term. So I need the derivatives at the value of the derivatives at x equals to 0, since this is a Mclaren series. Now I already have that y of 0 is negative pi over 2. So the first term in my Mclaren series is negative pi over 2 over 0 factorial, and 0 factorial is 1, so that is negative pi over 2. Now, however, y prime is y tan x plus cosine x. So evaluating y prime at 0. So y of 0 is negative pi over 2 times tan of 0 plus cosine 0. Now, tan of 0 is 0, so that term cancels out, and cosine of 0 is 1, which leaves me with the second coefficient of the expansion to be 1 over 1 factorial, which is 1. So that is my first coefficient, that is my second. Now, over here, since I want it up to the term in x squared, then I still need to find the second derivative. So if this is the first derivative in terms of y and x, so now what I would do is find the second derivative by just differentiating this function or this expression with respect to x. So y times tan x, we can see this as a product, so it's in the form u times v, where the derivative is u prime v plus v prime u. So let me rewrite this. So this is in the form u times v, where the derivative is u prime v plus v prime u. That's the product rule of the derivative. So u prime, which is y prime times tan, plus v prime times u, the derivative of tan is secant squared, so that would be y secant squared x, and the derivative of cosine is negative sine. So the second derivative at 0. Now tan of 0 is 0, whatever y prime is, so the first one is a 0. And secant of 0 is 1. Times y of 0. Now at 0, y is negative pi over 2, so that is a negative pi over 2 minus 0, so that's a negative pi over 2 for the second coefficient, but for the second derivative at 0. So don't forget that the second coefficient would be the value of the second derivative divided by 2 factorial, which would give me negative pi over 4. So now I can say that the solution to the differential equation is approximately negative pi over 2 plus 1 times x minus pi over 4 x squared. So this is the Mclaren series that is representing the solution to the differential equation up to the term in x squared.